I am Thibaut, and I will be moderating the different talks today. So in order to frame and articulate the different considerations, we essentially focused on three axes that are going to pace the speed at which maturation occurs. The first axis is the one that we've discussed together with Mark, is focusing on vineyard and environment, or better said, how the environmental stresses, whether looking at soil conditions or atmospheric conditions, are modulating vineyard performances in terms of biomass production, but also in terms of photosynthesis activity. Then the second axis is focusing on the relationships between plant and fruit maturation. We know that the footprint of environmental stresses is going to upregulate or downregulate genetic activation of maturation. Therefore, it's completely logical to expect that the history of plant stresses early season should impact late season the chemical composition of the fruit. And that will be discussed by Nicolas Bernard and Tori Harvik. And then, because at the end of the day we are growing fruit, not plant, it's important to understand how the fruit characteristics will drive different choices in terms of winemaking, and this will be discussed with our panels of winemakers. Also, with the same idea to frame the discussion and logically articulate cause, consequences, or carryover effects, we slice the season into 5 steps, and we've been doing that slicing everywhere, whether we look at the plant response in Burgundy, in Oregon, or in Southern California. Essentially, those 5 different colors corresponds to key stages that are setting up the pace at which the plant is preparing the next stage. So during the phase 1, essentially from leaf fall to bud break, the vine is dormant, and there is a lot of plant sensitivity towards heat and moisture control. So even if the plant is dormant, it's still sensing some environmental signals. Phase 2 is essentially the one that starts from bud break and ends when a leaf area peaks. And from phase 2 to phase 3, we are in this sweet spot, typically middle of June, middle of July, during which stresses, deficit of nitrogen, deficit of water, or even disease pressure, will drive what's happening during phase 4, which is now looking onto the fruit. So phase 3 ends at veraison, and phase 4 ends at the end of active sugar loading. So for those of you who are not very familiar with this concept, Nicolas will discuss it. And phase 5 is really this refinement of berry skin composition after technological maturation has been reached. And by technological, I meant sugar and acids, or in other words, the primary metabolites. Once they have been acquired by the fruit, what's left is the polishing of the tannins, the copigmentation, and all those tannin size reduction or modulation that happens during phase 5, which is where harvest decisions are most impactful. And to keep on discussing according to this timeline, we have a battery of plant indices that we can monitor the variations thereof in order to understand earlier on the footprint of the season. Typically during phase 1, we can look at wood indices such as shoot number, shoot diameter, or the fusion of the both, which is the wood index. During the phase 2, we can look at the speed at which leaf area unfolds. During the phase 3, it's time to look at when nitrogen accumulation is peaking. It's time to look at how the combined effect of light interception with leaf area development sets up the total amount of water the plant can use, which is the KCB max, which we will be discussing. And then during stage 4, we can look at the speed at which sugar accumulates as the way to differentiate different vintages. And during stage 5, we reach the peak of color, and we will see how we can use that information, looking at the time profile, to further refine the positioning of harvest. So in order to keep that time frame, we are going to intertwine, Mark Greenspan and I, our conversation. So we will talk about period 1, 2, and 3 together. And then we will move on to stage 4 and 5 to focus more on the fruit. So with that being said, what it is we're going to be seeing. So essentially, I'm using here the slicing of Sonoma into the distinct regions where we have networks of environmental sensors looking at global radiations or vapor pressure deficit or wind speed, rain amount. And what I have been doing, instead of showcasing each region separately, I've been looking statistically at the trends coming from those different regions. And after looking at the statistical distribution, I have simply chosen to show you the higher and the lower groups of patterns. So obviously, we don't have a dense network of weather stations in each and every region, but it should give you a good idea of the trends. And with that in mind, let's look first at what drives the explosion of vegetation at the beginning of the season. It's temperature accumulation and water supply. So if we focus on period 1 and 2, from a rain standpoint, the wettest area we've been able to identify are Dry Creek, Knights Valley, and Alexander Valley. So those top 3 regions were the ones that received the greatest amount of water. So you see we are above 1,200 millimeters of water, with Dry Creek showcasing the highest amount. But what I'd like to hint at is, even if we know it's a footprint of the year to have had a lot of water, look at what happened in the less wet area. You see that Carneros, Chalk Hill, and Sonoma Coast, depending upon where you were collecting water, were having still a lot of water, but significantly less than Sonoma. And that's already what makes Sonoma vintage characterization extremely difficult, because even looking at rain distribution, we see an extremely heterogeneous pattern, which means that we will have to adjust our appreciation according to site specificities. So lots of heterogeneity between appellations, you see, from 600s to 1600s millimeter. So in conclusions, when we are going to try to decipher the potential for growth, the potential for high yield or quick maturation, we need to know that what's going to drive the shoot elongation rate is not going to be limited by water. It's going to be limited by temperature accumulation, nitrogen accumulation, or disease pressure. So, because of that, let's now look at heat accumulation by looking at temperature profile cumulated, again, over all the regions, but slicing the high heat accumulation sites into 2 categories. So you see here the categories of the rapid accumulation sites, with Dry Creek and Knights Valley being on the top of it. And you see that those guys are typically seeing during period 2, so the period that goes roughly from bud break to the solstice, March 1st, June 21st here. And obviously, if you have no moisture deficit, when you have a faster heat accumulation profile, you expect the plants to, according to the civil calendar, growing faster. On the other side of the spectrum, the lowest heat accumulation areas were Sonoma Coast and Russian River, with barely 400 growing degree days accumulated. So with this simple approach, looking at heat and rain, we can come up with our first take-home of the day. There will be 6 take-homes. But the first one is that during period 2, so the period during which we have this explosion of biomass, growing degree days accumulation is very similar to 2016. So the speed at which things unfold should be following the same pattern. But we need to acknowledge that there is a very strong heterogeneity. Warmest areas being Dry Creek, Knights, followed next by Chalk Hill and Alexander Valley. And we know that doesn't mean only an earlier leaf area development in warmer areas, what's going to be more interesting to start factoring in is that the speed at which leaf area develops also drives the speed at which nitrogen is being accumulated into the leaf area, which directly drives the timing of your assessment for nitrogen or nutritional needs, and also the timing of your corrective actions, which I will discuss later. Since nitrogen and water are expected to be non-limiting, we had a lot of moisture in the soil, so therefore a lot of microbiological activities to convert nitrogen mineral into plant-available nitrogen. We expect, simply based upon this simple climatic characterization, that a larger transpiring leaf area should be produced. We will see if it is true based upon a general assessment, but before diving into that general assessment, it's my pleasure to invite Mark to have, through his eyes, a more practically focused presentation. So Mark will come discussing period 1 to 3. I will come back and Mark will discuss period 4 to 5. So Mark, thank you for being there with us.